In the previous session, we have discussed about AC applied to series LCR circuit. In that, we have got equation for impedance of the circuit, and that equation was Z is equal to square root of R square plus C minus XL whole square. And in explaining the concept of LCR, I told you that there will be a phase difference between the supply voltage and the current flowing through the circuit, and that happens because of the presence of capacitor and inductor in the circuit. So if the value of XC means it is called as a capacitive reactance, and its value, if it is greater than the XL, then the whole circuit will act like a capacitive circuit. I mean, the series LCR circuit will act like a pure capacitive circuit. In that case, there is a phase difference between the supply voltage and the current flowing through the conductor, and where in particular current leads the voltage. If the XL is greater than XC, then the circuit will be a somewhat inductive circuit. So in inductive circuit, there is a phase difference of pi by 2. In particular, current lags the voltage by pi by 2. That is why there is a phase difference of pi by 2 between current and voltage. And also we have took another case that if XC is equal to XL, if the capacitive reactance becomes equal to inductive reactance, in that case what happened is we got the equation for impedance as Z is equal to R, because the equation for Z is R square plus XC minus XL whole square. If we put XC is equal to XL, XC is equal to XL, then we will get this whole term will be equal to 0 because these are equal, and R square to the root, so square and the roots are cancels each other. So that is why we will get Z is equal to 1. So since Z is decreased 1, so we can say the maximum current will flow through the circuit, so that whatever the phase difference between current and voltage exists in the series circuit becomes 0. So there could not be any phase difference between the current and voltages when XC is equal to XL, because in that case high amount of current will flow through the circuit. And this is, I told you that this is called as a resonance. So resonance means it is a very common thing which you can hear in physics. We already learned about the resonance in our first year. So resonance means it is nothing but a maximum vibration of any particle. So that this resonance it is exhibited by all the materials which present in our nature. All the materials have their own natural frequency of vibrations. So whenever applied frequency, if you have applied a external frequency, external force, if the frequency of vibration of the external and the natural frequency of vibration of that body equal, then that body will vibrate with the maximum amplitude. So this condition is called as a resonance. So that is why what we can say is, in resonance condition, amplitude of the quantity will be maximum. Okay. So here, if we come to the series LCR circuit, I told you that XC, whenever XC is equal to XL, then Z is equal to R. Because of that reason, I is equal to, we know the value for Im is equal to Vm by Z. the Z is decreased. As it decreases, Im will increase. So current reaches its maximum value. So this is we call as a maximum value current, or this is also called as a current amplitude. That is why current amplitude will be maximum when Xc is equal to XL. So this is known as a resonance. And this resonance condition can also be obtained by varying the frequencies. Actually, the main use of this resonance is in radios or televisions. I already told you the example of radio and television, that these signals are sent by one station with a particular frequency. So whatever the frequency sent by these stations to be received by the antenna that we have in our TV or in the radio. So the antenna of our TV or radio will receive all kinds of frequencies. There are a lot of there are different values of frequencies we can see in our nature. So this antenna will receive all kinds of frequencies, including the frequencies that sent by those stations. So then how to identify that particular frequency? Because we don't need all other frequencies, we only need the frequencies of that station, that channel. Then how to tune that channel? So in radio, what you will do, if you, for example, if you want to tune a channel, if you want to hear one channel, then you will rotate the knob. So as you rotate, you will listen the channel. You can clearly hear the sound of that channel. So the process happening behind it is you're tuning the channel means you're selecting one frequency. So the main thing which is happening behind is the resonance condition. You are tuning the channel means you are rotating the knob means you are varying the value of capacitance. So as you vary the value of capacitance, you will set one frequency. That frequency will be equal to the frequency that is received by the antenna. That frequency is exactly the frequency of the channel that's sent by the station. As an example, if the 550 Hertz is the frequency of a channel that is, if it is sent by the station, if it is a red I will see frequency of a red then we will rotate the knob. We are change the value of capacitor to set one frequency in our circuit, and which frequency becomes nearly equal to this frequency. If this happens, then resonance occurs. That means current reaches its maximum value. So at that frequency, Xc will be equal to XL. And so at that point, current reaches to maximum. You can clearly listen or you can clearly watch that channel. So this is called as a resonance. So these are the applications of this concept, that is resonance. Yes. So I told you that at resonance condition, current reaches maximum. And also I told you at resonance, capacitive reactance is equal to inductive reactance. Okay, let us take this one. Xc is equal to XL. X is equal to 1 by omega naught C. Then XL is equal to omega L. Now let us write omega together. Take the L to the L like this, and by rearranging omega into omega, that becomes omega square, that is equal to 1 by LC. So omega equal to, you can write, take the square root of it. So So that is why you can write 1 by square root of LC. So omega is equal to 1 by square root of LC. And this can also be written as omega naught. Okay? This can also be written as omega naught. And this frequency is a value of angular frequency. And this frequency is called as a resonant frequency. So I told you that we have to set one frequency. That is this one. This is a resonating frequency. If the resonating frequency is equal to the received frequency, then the particle or the current in the circuit will reach to maximum. So that condition is called as a resonance. Okay? Resonance is a condition is a condition in which if condition in which capacitive reactance equal to inductive reactance then current reaches to maximum. Current reaches to maximum. So the frequency, this frequency omega naught is called as a 1 by is called as a resonant frequency. At that condition, maximum resonance occurs, or I can say current amplitude is a maximum. Now let us see the relation of resonant frequency and the current with the graphical method. Already we know the equation for resonant frequency, that is omega naught is equal to 1 by square root of LC. And at the resonant frequency, current in the circuit will be maximum. That is why current and the resonant frequency or the frequencies are related to each other. That is why we can show a relation between the current and the frequency of the graph. So to explain the relation between this resonant frequency and the current, we need a graph with the two axes. Along one axis, we have to take a current, a value of current along the one axis, and along the another axis, let's take value of frequencies. Now this is the graph. Sorry, this is the two coordinates along which we have taken omega as well as I. Now, this is a case for a series LC circuit in which we have capacitor and the inductor. So that plays a major role in the LC circuit. So in that circuit, current will flow. Current has to flow in the circuit, and the current in that circuit will be maximum when the RC circuit adjusts to a frequency called resonant frequency, or in other words, at resonant frequency, current in the circuit will be maximum, and this is going to happen when XC is equal to LCR. Yes. See here, we can see different values of current here, but at one point there is a maximum current. See here. So if I take a point along this graph, I can take many points over here, and if we take the points, we can write the corresponding values of omega also. For different frequencies, there are different values of current. But at one particular value, let's say that as omega naught, at one particular value, the value of current observed to be maximum. So this is the maximum value of current. Let's write that as IM. IM means it is a peak value or maximum value. So this is that peak value of current is operating only at one particular frequency, that is called as the omega naught. Now, and this particular frequency omega naught can be adjusted with the combination of LNs. So those circuits can also be called as a LC circuits, and these circuits are mainly used in the communication purposes. I mean, they are actually used in radios and the televisions to receive the signals. So in the LCR circuit, by adjusting the values of L and C, we can select the values of one frequency. If that frequency, that can be called as a resonant frequency, if that resonance frequency becomes equal to the frequency of any object, then resonance happens. Okay, like it. Now this we know only one value of frequency. Now, if we wanted to select any other two values of frequency, or in other words, what we can say is, if you wanted to select a range of frequency. So in the case of radios, there will be a range of frequency. In between, we can receive all kinds of signals. And all that signals will be sent by that radio stations. So in order to select a range of frequency, we need something arrangements. We need some we have to take some rules are there. So what is the rule to select a range of frequencies? I told you range of frequencies taken. If we take the range of frequencies, then all the frequencies within that region is accessible by the receiver of our device or by the LC circuit. Yes. Then how to take a range of frequencies? So to take the range of frequencies, we need one value of current, and value of that current is multiplied by 1 by root of the maximum value. What is our maximum value of current? That is I. That should be multiplied by 1 by root 2. And we should take that value. Let's say this is that current. That current is equal to Im divided by root 2. Means Im is maximum value of current is multiplied by root 2. At this current, we can write two values of frequencies. Let's name it as omega 1 and omega 2. Okay, and these frequencies, omega 1 and omega 2, are called as half power frequencies. Then why it is called as a half power frequencies? Power is half. Because, see, when the current in the circuit reaches a maximum, at that condition, Xc is equal to Xc. So, power dissipated in the circuit will also be maximum. There is a maximum power dissipation in the circuit at the resonance condition. So this is a point at which power dissipation in the circuit is maximum, which is actually through the resistor. Why? Because Xc is equal to XL. That is why. So there is a maximum power dissipation. Now these are the two values of frequencies at which power is reduced to half of its initial value. So to reduce the power to half of its initial value, we need to multiply the maximum value of current with the 1 by root. So this is a concept. If you multiply the maximum current with the 1 by root 2, we will get two values of frequencies, and those frequencies are called half power frequencies, because these are the frequencies at which the current, maximum value of current is Im by root 2. And those frequencies are called as a half power frequencies. So if you look at this, see, these are the range of frequencies. So this is the range from omega 1 to omega 2. What is, how to find that range of frequencies? We have to see that. So if you set these range of frequencies in our receiver circuit, means in our radio, so that you can accessible all the signals which comes in between these frequencies. So this is the usage of the taking the range of frequencies. Okay. Then what is the range of these frequencies? How to call that? We need to understand. Let's say there is the difference between the omega naught and omega 2. Let's call it as a delta omega. There is a difference between delta omega between omega naught and omega 2. So frequency difference between omega naught and omega 1 also delta omega. Let it take like that now. And if you look at this, omega 1 means it is a value from this 0 to this point. Omega 2 means it is a value from 0 to this point. So, how to write the value of omega 1 and omega 2 then? Now, let's write from figure omega 1 equal to, see here, from 0 to this point omega naught, and then what will be omega 1? So what you can write? I can write omega naught minus delta omega. You can see delta omega is this, omega naught is this. If you subtract the delta omega, you will get omega 1. So this is what? Similarly, how to write the omega 2? Omega 2 is equal to omega naught plus delta omega. Omega naught plus delta omega. So this is equation number 1, this is equation number 2. Now subtract 2 by 1. Let us subtract this equation by 1. That is omega 2 minus omega 1. That is omega naught plus delta omega minus of omega naught minus delta omega. So this is equal to omega naught minus omega naught. They cancels. Delta omega naught, omega and minus of minus plus delta omega. That is why you will get 2 delta omega. See what we have found? We have found the difference between the two half power frequencies. These are the two half power frequency values, and their difference is equal to 2 delta omega, which is actually called as bandwidth. Bandwidth. It is a band, it is a range, it's a range of frequencies, and that has some width, bandwidth. So this is called as bandwidth. So the value of bandwidth is 2 delta omega. Then how to define this bandwidth? Bandwidth is the difference between the two half power frequencies. It is a difference between the two half power frequencies called as a bandwidth. It is the difference between two half power frequencies. Half power frequencies. And the value of bandwidth is called as a 2 delta omega. Now let us study some more things. Let us study some other features of this graph. Let's again look at this. We know the equation for bandwidth. This is a bandwidth. If the bandwidth is very less, if the bandwidth decreases, if this range decreases, what will happen is we will get a very sharp curve. Curve will be very sharp. If the bandwidth increases, width decreases like this. What happens is the sharpness will decrease. There will be, the curve is no more sharp. Okay, again I am repeating this concept. If the bandwidth is very less, the curve is more sharp. The bandwidth is increased, then the curve is less sharp. If the curve is less sharp, then resonance condition is not so clear, because resonance means there should be a one particular frequency At that frequency, current should reach its maximum value. So, what will happen is in radios, in the receiver of the radios, we can clearly tune a channel, because if the curve is very short, then we can particularly tune a one channel. If the curve is not so sharp, then it is not able to receive the particular channel, not able to hear the particular channel, because in that region we have many frequencies. So that is why this feature is very important here. That is the sharpness of this curve, and this can also be called as quality factor. Quality factor means it is the quality of that curve. What a quality? Quality means whether the curve is sharp or not. And this sharpness of the curve depends upon the bandwidth. And that sharpness of a curve can be obtained, sharpness of resonance, or quality factor. Quality of that curve. Sharpness of this resonance or quality factor, that can be calculated as Q is equal to, it can be calculated as by the ratio of omega naught divided by 2 delta omega. It is very simple. Omega naught means it is called as a resonant frequency, and 2 delta omega called as a bandwidth. It is a ratio of resonant frequency to the bandwidth is called as a quality factor or sharpness of resonance. See, if the 2 delta omega value decreases, what will happen to the Q? Q will increase because they are inversely proportional. That means if the width decreases, quality increases. Means there will be more sharp in the graph. That is why we can clearly access the channel. So there will be no overlaps from other frequencies. So this is the feature of this resonance curve, and that is called as a quality factor or sharpness of resonance. And this can also be written as omega naught divided by 2 delta omega is there. This quality factor is also equal to 1 by omega naught CR, or 1 by omega naught CR, or we can also write this as omega naught L by R. Omega naught L by R. So these are some other form of equations for quality